Good afternoon, everyone. We are pleased to present our work, WaterFormer, a global local transformer for underwater image enhancement with Environment Adaptor. Here is an overview of today's presentation, which will cover the introduction, proposed method, experiments, discussion, and conclusion. Let's begin with the introduction. Underwater image enhancement, UIE, is vital for underwater robotic vision. While CNN-based methods struggle with capturing global context, transformers excel at this, but face challenges like coarse details and adapting to diverse underwater conditions. To overcome these issues, we propose a novel, transformer-based UIE network. Let's now take a closer look at our proposed method. The overall design of our proposed WaterFormer is illustrated in this figure. The degraded underwater image is first processed by a 3x3 convolutional layer to extract low-level feature embeddings X0. These features then pass through K-encoder stages, each focusing on local information. After the encoder stages, a bottleneck stage with LBGL trans blocks processes the deep features. The GL trans blocks in this stage include an environment adapter, enhancing adaptability to diverse underwater conditions. The decoder stages mirror the encoder stages, progressively reconstructing clear underwater images. Unlike traditional enhancement networks, each decoder stage combines features from the upstream decoder and our DESC module. This figure illustrates the architecture of our proposed GL trans block, which consists of two parallel self-attention branches, a window-based local multi-head self-attention, LMSA, and a global multi-head self-attention, GMSA. After layer normalization, input features are sent to these branches, with the LMSA on the left and the GMSA on the right. We also introduce a feature modulator that adjusts the global and local features using weighted parameters. This figure shows the architecture of our proposed detail-enhanced skip connector DESC module designed to address the transformer's difficulty in capturing local details. Directly linking encoder and decoder features often results in the loss of these details. The DESC module begins with a 1x1 convolution to expand feature dimensionality, followed by a 3x3 depthwise convolution to capture local information. Finally, another 1x1 convolution gathers cross-channel context and restores the features to their original dimension. Effective UIE methods must address challenges like wavelength-dependent light absorption and backscattering, which degrade images in different underwater environments. As shown here, we add the environment adapter at the bottleneck stage before the LMSA/GMSA modules to leverage deep features that retain global environmental information. The core of the adapter is the learnable environment embeddings with shape L times C, where L is the number of environment types and C is the feature dimension. This improves feature map flexibility and enhances performance. Let's move on to the experimental results. Here are the experimental setups. We trained and tested our method on both synthetic and real underwater image datasets. This slide shows the quantitative comparison between our proposed method and other SOTA methods on various synthetic underwater datasets. Our WaterFormer outperforms the other methods significantly, with an average improvement of 2.27 dB in PSNR and 0.017 in SSIM. This figure shows a visual comparison of synthetic images under different underwater conditions from a synthetic dataset. The traditional prior-based method, UDCP, fails to fully enhance image quality, leaving water effects visible. Other learning-based methods show color distortions or noticeable artifacts. In contrast, our method produces images that closely match the ground truth, with higher PSNR and SSIM scores. These are the quantitative results of our method on real-world underwater images. The table on the left presents reference metrics, PSNR and SSIM, while the table on the right shows non-reference metrics, UIQM, UCIQE, and results from a user study. Both tables demonstrate that our method outperforms other SOTA methods. This figure illustrates visual comparisons in greenish and bluish underwater conditions. Real underwater images pose greater challenges than synthetic ones due to their complex environments. In these scenarios, UDCP inadequately addresses the color variations, often leading to darker tones. Methods like SwinIR, SyriaNet, U-Shape Trans, and WaterFormer tend to generate noticeable artifacts. GLNet and Restormer are less effective in eliminating greenish-bluish effects. Conversely, WaterFormer consistently improves image quality across various underwater conditions and achieves higher PSNR, SSIM scores with reference images. This video further demonstrates that our proposed method achieves SOTA performance across various underwater environments. We conducted ablation studies to verify the effectiveness of each proposed module. The table on the left shows that removing any module results in a performance drop, while the figure on the right illustrates a noticeable decline in visual quality when a module is removed. Now we discuss the limitations of current UIE methods. As shown here, many current UIE methods struggle in complex lighting and highly turbid conditions. Therefore, additional efforts are needed to address these challenges. Finally, we conclude our work. In this work, we present a novel transformer-based network for underwater image enhancement. Our GL transblock effectively captures both global semantics and local details while maintaining computational efficiency. The DESC module enhances fine detail generation, and the environment adapter improves adaptability to different underwater conditions. Our code is now available on this GitHub repository. Thank you for listening.